Welcome to Lecture 2.5, Power Series Solutions to Differential Equations. Let's start with a simple example to motivate what we're going to do. So I call this beyond constant coefficients because this is the first second order ODE that we've seen where the coefficients of the y's are no longer constants, but they're variables. Now one thing you may notice is that these variables are x's instead of t's, and that's because this topic or the equations that arise in this topic generally come up in ODEs where y is a function of space instead of time. And we'll see more of this later, especially in the next few sections. So here's a simple example to start. Find the general solution to x squared y double prime plus xy prime minus y equals 0. So think about what's going to solve this. Think about what's not going to solve this. So I claim that an exponential function e to the kx is not going to work. And let's think about why that is, because if we try to plug that back in for y, and then here we get an exponential function, here we get x times e to the kx, and here we get x squared times e to the kx times a constant. That's not going to work. So what else is going to work? Well, how about this? I'm going to propose something and hopefully it will convince you why it will do the trick. Suppose y of x equals x to the r. So this is a power of x. And now look what happens when we plug this back in. So into this term we get x to the r. Now when we take the derivative we lose a power of r, but we get it right back by multiplying by x. So this term is going to have some number of x to the r's in it. And then this term, we take two derivatives, so we lose two powers of r, but then we gain them right back when we multiply by x squared. So I claim that all three of these terms are going to have x to the r's in them, and again, that's because for each time we have a derivative, we have an x out in front. Okay, so let's figure out what r is going to work. So y prime of x equals r x to the r minus 1, and y double prime of x equals r times r minus 1 x to the r minus 2. So now let's plug these guys back into here. So this first term is x squared times this guy, so that's r times r minus 1 times x to the r. The next term, xy prime, that's x times r, so that's r times x to the r, so that's r times x to the r, then minus y, which is x to the r equals 0. So let's simplify this on the left hand side. So first of all, we can factor out an x to the r. There's going to be an x to the r in everything. And now what do we have left? We have an r squared minus r plus r minus 1. So what is that? That's x to the r times r squared minus 1 equals 0. So that tells us that r equals plus or minus 1. So we have two solutions. We have y1 of x equals x to the first, and y2 of x equals x to the minus first. So our general solution is y of x equals c1 x plus c2 x to the minus 1, or 1 over x. So we have found two solutions, and so we have the general solution. So this was a simple example. I did this so the roots would be nice and distinct and real and also very simple, but you can imagine that there are two other cases when you have complex roots of the form a plus bi, and also when you have a repeated root. Now, I'm not going to do examples of all three of these cases. If you want to see them, I would encourage you to go to my Intro ODEs course, and I have a lecture on Cauchy-Euler equations, because that's what this is. Here's the definition. A Cauchy-Euler equation is an ODE of the following form: a x squared y double prime plus b x y prime plus cy equals 0. So for all of these, as above, we assume that there is a solution of the form y of x equals x to the r. And if we plug this back into the ODE, then we get a degree 2 polynomial in R, just like we did before. Now, I'll note that it's not quite as simple as just copying these coefficients, a, b, and c, to make the polynomial like we did when they were constant coefficients. For example, up here, in our first example, our coefficients were 1, 1, and negative 1, and our polynomial ended up being x squared minus 1. So it's not quite as simple. You have to be a little bit careful, but it's also not hard. You just plug it back in. But as before, there are 3 cases. Distinct real roots. This is like what we did in example 1. Suppose those roots are r1 and r2. Then the general solution is y of x equals c1 x1 to the r plus c2, c1 x to the r1 plus c2 x to the r2. When there are complex roots, let's call them a plus bi. Then, as before, you could write the general solution as c1 x to the r1 plus c2 x to the r2, but that's not desirable because what does x to the a plus bi actually mean? So in this case, what you should do is you should use Euler's identity. Recall that as e to the I theta equals cosine of theta plus I sine of theta. Well, now hold on. What do I mean by e to the I theta? There aren't any e's in here, are there? So what? I'm not going to spend long doing it, but so what would you do? So x is, let's see, what is it? E to the natural log of x, right? So if I do, so x to the r is e to the natural log of x times r, which is e to the r natural log of x. And now if you use Euler's formula here, so you can write this as cosine of r times natural log of x plus sine, plus I sine of r natural log of x. And that's where this comes from, this b natural log of x and sine and cosine. Finally, in the case when there's a repeated root, you get something a little different than just sticking a t in front. It's similar. Y of x equals c1 x to the r plus c2 x to the r times the natural log of x. And another way to see this is you can do a variable substitution where t equals natural log of x, which actually turns this ODE into one with constant coefficients, and that's where this natural log of x comes from. So again, if you want to see details in this, and if you have not seen these before, I would strongly encourage you to look at my lecture on Cauchy-Euler equations from my Intro ODEs course. I do all 3 of these examples in detail. The topic of this lecture are power series solutions to ODEs. So that suggests that these are going to be more complicated. So I want to give you a harder example than the Cauchy-Euler ones from the previous slide. So find the general solution to y double prime minus 4xy prime plus 12y equals 0. Now the thing to notice here is, well, let me ask you, does y of x equals x to the r, is that going to work? Well, let's see. So if we plug that into this last term, we get 12 times x to the r. If we plug it into this term, we get, well, the y prime means we lose a power of r. So let's try that. Y prime of x equals r x to the r minus 1. But then we multiply it by x and we get that power right back. So this term is also some number times x to the r. But the problem is that this y double prime, this is not going to. So in other words, if we try to plug this in, we're going to get r times r minus 1, x to the r minus 2, minus 4 r x to the r plus 12 x to the r equals 0. And what's the problem here? we can't ever make these x to the r's cancel with this x to the r minus 2. That is not going to work. So we have to do something else. So here's, maybe it's not the first thing you would have thought of, but I'm going to assume, so this thing has solutions to it. It has two solutions. The general solution is a two-dimensional vector space, but we don't know what those functions are. And unfortunately, functions that we're used to, like sines, cosines, logs, exponential functions, those are very, very special functions. Most functions don't have nice names like that, but most functions can be written using a Taylor series. So we're going to assume that we have this unknown function that is, say, n equals 0 to infinity of a n x to the n. So think of this as its power series representation. And what we want to do is figure out what the an's are. So let me take two derivatives of this. So y prime of x equals n equals 0 to infinity of n a n x to the n minus 1, and y double prime of x equals n equals 0 to infinity of n minus 1 a n x to the n minus 2. And now let's plug this back in. Well, before I do, let me just write out this first power series just so you can see what it looks like. Sometimes it helps to see it written differently. So this is a naught plus a1x plus a2x squared plus a3x cubed plus etc. And by the way, just what's the derivative of this? So let me see. So y prime of x, so the derivative of that is this thing. And from this, it looks like you would start at an x to the negative 1 term, but just look at this and take the derivative term by term. What happens? Well, you get a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus ... and so on. So this isn't as mysterious as it seems. So let's plug these guys back into here and see what happens. So y double prime is, so let me say that, I'm going to plug back in. So y double prime, actually let me not write out y double prime, I'll just write out what it is. So I'll say that n equals 0 to infinity of n times n minus 1 times a n x to the n minus 2 minus 4xy prime. And I'm going to take this x and I'm going to stick it here so this n minus 1 becomes an n. So this is 4 times the sum from 0 to infinity of n a n x to the n. Notice the n, not the n minus 1 because of this x here. And then plus 12y. So plus 12 times the sum from 0 to infinity of a n x to the n equals 0. Okay, so now what can we do? We can combine these two sums into one, and we would like to be able to combine these three sums into one, but the problem is that this is x to the n minus 2. And we can't combine that with x to the n. Now, so what can we do about that? If you think about what this thing really is, I mean, I'm going to write it up here. This is the second derivative. It's just the derivative of this guy. So this is actually 2a2. So the derivative of this is 2a2. The derivative of the next one is plus 6a3x plus 12a4x squared. Plus, and the next one is going to be not 4 times 3, but 5 times 4, plus 20a to the 5th x3. Now, what's a formula for this? Now, this coefficient is 2 times 1. This is 3 times 2. This is 4 times 3. This is 5 times 4. So we should be able to write a formula for this, like not going from, without an n, x to the n minus 2, but just from x, the 0th power up to the, just as the power series. So here's what we're going to do. I'm going to take this. I'm going to say, I'm going to change variables. Let m be equal to n minus 2. So I'm looking at that and I'm saying I'm going to call that m. If I do that, then n equals m plus 2. So I can write this. So every time I have an n, I can replace it with m plus 2. So I can write this as the sum of m plus 2 times m plus 1 times a m plus 2 times x to the m. And we're going from 0 to infinity, right? Well, technically, we're actually going from when n equals 0, when n equals 0, m actually equals negative 2. So should we really go from negative 2 to infinity? No, we don't need to, because look, this second derivative thing starts at the 0th power. So why is that m equals negative 2 really there? That's because these first two terms, this is the x to the 0th term, this is the x to the first term. When you take derivatives of those, you lose two powers. So this technically goes down to, this x to the 0th term goes down to an x to the minus 2th term, but it becomes 0 when you take the derivative of this. And similarly, you take the derivative of twice of x to the first, that goes down to x to the 0th and then x to the negative 1, but the constant is 0. So we can ignore those first two terms. So here's what we have. So we have this guy minus 4n equals 0 to infinity of n times a n x to the n plus 12 n equals 0 to infinity of a n x to the n equals 0. Okay, so now what? Well, this is x to the m, this is x to the n. Can we combine those? Yeah, why not? This m, this is a dummy variable. It doesn't matter if we call this m or n or k or j or c or something else. This is just a variable. So if I want to, I can write this as n plus 2, n plus 1, a n plus 2, x to the n, and make that an n. There's nothing wrong with doing that. And if you don't believe me, come up to the top and let me ask you, or I'm going to convince you that this power series, x to the n, is completely equal to m equals 0 up to infinity times x to the m, which is the same as k equals 0 to infinity of x to the k. There's no difference. It doesn't matter what we call that dummy variable. So anyways, now we're going to combine this into a single term. I'm going to write this as n equals 0 to infinity of, let's see, I'm going to factor out this x to the n. So what goes right here? So there's this term, and that term. So there's n plus 2, n plus 1, a to the n plus 2, minus 4n a to the n plus 12 a to the n. This guy times x to the n equals 0. So now what? So what does this tell us? So this is a power series. This is a infinite series of powers of x. And if that power series equals 0, then it better be the case that every single one of these coefficients has to equal 0. Okay? So what does that mean? That means that, well, let's set this equal to 0. So, and then what? Well, I want to solve for these coefficients. So I'm going to write this as, I'm going to solve for a n plus 2 as, so let's move this over to the right hand side of 0. So a n minus 2 equals 4 n minus 12 over n plus 2 times n plus 1 times a to the n. So this is called a recurrence relation. Okay, so it doesn't tell us what the coefficients are, but it says if we know what the nth one is, here's a formula for the nth plus 2 coefficient, and so on.
Let's summarize where we are so far. So we have this ODE that is not constant coefficients, because there's this x right here. We assume that this has a power series solution of the following form. So we take the derivatives of this and we plug it back in, and we get, well, let's see, so we get an x to the n in both of these terms, but we only get an x to the n minus 2 in this first term, so we don't have an x squared in front of there to make up for that. So we can't combine terms, so we have to shift the indices of this first term, and when we do that, we get an x to the n in every term, and we set we combine coefficients and we set that equal to 0 because the right-hand side is the 0 function. So we get that, we get this equation involving an plus 2 and an, and we can solve for an plus 2 in terms of an. That's called a recurrence relation. So this gives us a formula for an plus 2 in terms of an. So if n equals 0, and this is, we can then, if we know in advance what a naught is, then we have a formula for a2, for a4, for a6, a8, and all of the even ans. And similarly, if we know what a1 is, then we have a formula for all of the odd ans. Now notice that if the power series y of x is a naught plus a1x plus a2x squared plus a3x cubed, and so forth, notice that y of 0 equals a naught, and y prime of 0 equals a1. So if we think about what this means, a naught is like the initial position. And if we take the derivative, then that goes away, and we get a1 as the constant term, and we plug in 0, that's y prime of 0. That's like the initial velocity. So in other words, specifying the initial position and the initial velocity determines all of the later coefficients. So that's not surprising, because we know that there are 2 degrees of freedom, or there's a basis of 2 solutions for the second order ODE. So let's do an example, or let's do this explicitly. So let's suppose that n equals 0. We get that a2 equals 4 times 0 minus 3 over 2 times 1 times a naught, which is negative 6 a naught. I'm not usually going to multiply this out. I'm more worried about factoring it like this so we can see the patterns. You'll see what I mean shortly. So when n equals 2, we get that a4 is 4 times 2 minus 3 over 4 times 3 times a2. And, well, we can plug this guy in for a2, and then we get 4 squared times 2 minus 3 times 0 minus 3 over 4 times 3 times 2 times 1 times a naught. And now you might see a pattern developing. If n equals 4, we get a6 equals 4 times 4 minus 3 over 6 times 5 times a4. Once again, we plug that whole guy into a4, and we get 4 cubed times 4 minus 3, 2 minus 3, 0 minus 3 over, I'll write this as 6 factorial. That's 6 times 5 times 4 times 3 times 2 times 1 times a naught. Now, I could multiply these out, and if I do, this becomes 2 a naught, and this becomes 4 fifteenths. That's supposed to make sure that the 4 fifteenths a naught, but I think it's better to just see the pattern like this. So let's suppose that we set a1 to be 0. So the initial velocity we say is 0. If we do that, then our power series solution has only even terms. And we can write out what that solution is. So I'm going to call that y0 of x It's the sum over all even n. And now let's write a formula for these coefficients. So notice that when I have a 6, I have a 4 cubed. A 4, I have a 4 squared. So I'm going to have 4 to the n over 2 here. Then I'm going to have n minus 2 minus 3, all the way down to 4 minus 3, 2 minus 3, 0 minus 3. And this whole thing is going to be over n factorial. And now I have a naught x to the n. So this is a solution. Now usually we write solutions to second order ODEs, general solutions, as like c1 y1 of x plus c2 y2 of x. So what I could do is I could take this a naught, I could pull it out of the sum, and I could call it c1 if I wanted to, or c naught. And then what I'm left with is an actual explicit function as a power series. Okay, so let's do the odd terms. So if n equals 1, then we get a3 is 4 times 1 minus 3 over 3 times 2 times a1. And that is, what is that, negative 4/3 a1. And if n equals 3, then we get that a5 is 4 times 3 minus 3 over 5 times 4 times a1. That's equal to 0. So if n equals 5, we get that a7 equals, I don't know, something times a5, but a5 is 0. So we get this is equal to a9, a11, etc. All of the odd terms are 0. I definitely set this up this way intentionally. So now let's look at the odd terms. So y1 of x. So now suppose we say that a naught, what if we let a naught be 0? That's going to kill off all of the even terms, and I'm left with the odd terms, which is just 2 of them. It's just a1 of x and a3 of x cubed. So the odd terms, a to the n, x to the n, is really just 2 terms. So that's a1x plus a cubed x, a3 x cubed. And a3 is negative 4/3 a1. So minus 4/3 a1 x cubed. And if I want to, I can write this as a1 times x minus 4/3 x cubed. So let me call this, well, so look back to c1y1 plus c2y2. Again, think of y1 as, I guess I'm calling this y1, but this y1 up here is analogous to what I get if I pull this a naught out of here, call that c naught, and then what I'm left with is y1. Here, y2 is just a polynomial. This is no longer an infinite series, but we have a basis of solutions. So let me write this down. So a basis of the solution space is even n, 4 to the n over 2, n minus 2 minus 3, dot, 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 2 minus 3, 0 minus 3, over n factorial, times x to the n, and x minus 4/3 x cubed. So here are 2 linearly independent solutions that form a basis for the solution space. Now, when there's a solution like this, you don't really need to go into this detail and write those 2 solutions. It's perfectly fine to just say there's a power series solution, this is the recurrence, because from that we know everything. So what I'm doing down here is not always necessary unless I actually specify it on a homework assignment, but I think it's a worthwhile exercise to do because it helps you understand the structure of these two things better. One more comment. Sometimes if you look at books or on the internet, you will see these power series like this when there's just even terms written differently. For example, you can write, if you want to, you could write this as a sum from n equals 0 to infinity times, I don't know, something times x to the 2n. And the 2n is up there, so it skips all of the odd terms. And then this, now you can't just use this coefficient. You have to think about what that is. Like, for example, if this is n, so this n over 2 is half of that. So in here, there's going to be let's see, maybe I shouldn't have written this line here. Let's see. Let's pretend that's a fraction. So what's on the bottom of the fraction is going to be a 2n factorial, because we have this that n has to match that n, and then on the top of the fraction, well, this is going to have to be a 4 to the n, and then what's going to go in here? Let's see. So this is actually, and I'll just tell you what's going to go in here. I didn't plan this out, but so it's 0 minus 3. So it's going to start from 0 minus 3, 2 minus 3, and then what is this term? N minus, it's 2 minus this. So that's 2n minus 2 minus 3. So 2n minus 2 minus 3. So notice that this is just the same thing as this. It's just here I'm forcing the terms to be even, and here I'm saying even n. So this is just a notational thing. And usually books will favor this because it's cleaner, but there's a little bit of practice needed to go between these two, but I'm not going to worry about that too much. Let's summarize what we just did. So to solve this ODE, it's linear, homogeneous, but does not have constant coefficients, we took the following steps. We first assumed the solution was a power series. We plugged that power series back in to the ODE. We obviously had to take derivatives to plug it back in here. And then we combined what we had into a single sum. Each term was x to the n. Now we had to shift the coefficients on one of those terms because we had an x to the n minus 2. But from here we set this each coefficient equal to 0 to get a recurrence. That told us what an plus 2 was in terms of an and an minus 1. Well, in our case, it was simple. It was just in terms of an, but in general, you could have it in terms of both of these. So think about, let's try to, for practice, come up with a power series that's going to have both of these. So when we had a y double prime, when we plugged this back in, we had n equals 0 to infinity of n minus 1, an x to the n minus 2. So when we shifted, this gave us an a to the n plus 2. And then everything else had an an in it. But suppose we had also had maybe y prime. Now this would give us an n equals 0 to infinity of an x to the n minus 1. And if we had, so when I say y prime, I mean without an x in front. And that is going to give us an I don't want to say plus, is an a to the n plus 1. And then if we had maybe a y here, that's going to give us, again, n equals 0 to infinity of an x to the n. That's going to give us an an. So if we had this ODE, y double prime plus y prime plus y, some coefficients in front, we would have an plus 2, an, and also an an plus 1. So our recurrence would be a little bit more complicated. Now in that case, we could not split off the even terms and the odd terms, but we would still have two linearly independent solutions. It would be less clear exactly how those are related, but we still have the fundamental theorem that a solution to this ODE is going to have a basis of size 2. It's going to form a two-dimensional vector space. I want to conclude with an example from physics that we will return to several times in this course, especially when we study partial differential equations in spherical coordinates. So there's this partial differential equation, this PDE called Laplace's equation, which comes up in the heat equation and the wave equation both. And when you convert it into spherical coordinates, it gets more complicated, and when you solve it, you end up getting this ODE embedded inside, and that's this guy. So this comes up when you want to model something like the gravitational potential of a point mass or the Coulomb potential of a point charge, or it also comes up when you're solving Schrodinger's equation in spherical coordinates in quantum physics. So more on this later. We're actually going to use the solution that we get now in later lectures. Okay, so find the general solution of this guy. So let's assume that y of x is a power series, n equals 0 to infinity, of a n x to the n. And let's take derivatives. So y prime of x equals n equals 0 up to infinity of n a n x to the n minus 1, and y double prime of x equals n equals 0 to infinity of n minus 1 a n x to the n minus 2. And let's plug these guys back into here. So I'm going to break this into two terms. So I'm going to write this as y double prime minus x squared y double prime. It's my experience that that's a little bit easier if we break these up. And often in the literature, you'll see these L's as being N's, but I'm calling them L's because I don't want to get confused with the dummy variable M or N that we're using. So we plug this back in. Let's see. So we get y double prime. That's going to be, which one is that? That's going to be n equals 0 to infinity of n times n minus 1 times a n times x to the n minus 2 minus n equals 0 to infinity. The same thing, except we have to multiply by x squared. So this n minus 2 is just n. This is n times n minus 1 times a n times x to the n minus 2xy. So that's this thing, but there's a 2 in front of it and this becomes x to the n. So let me put the 2 inside of that. N equals 0 to doesn't really matter. N, a, n. I almost forgot my 2. Let's put the 2 right there. And x to the n, and then plus this last term. So this is, I should say, this is minus x squared y double prime. This is minus 2xy prime, and this is plus l plus 1 times y. So this is n equals 0 to infinity of, let's go l plus 1 times a n x to the n equals 0. The way to think of these L's, there's one of these, think of it as harmonics. So for each, it's like for each fundamental frequency, there's going to be one of the, and more on that later, especially when we study Fourier series. Okay, so now we have x to the n in these three. This one we have to shift up by 2. So before we said, I'm going to actually do what we did before in one full swoop. So this is, if you're not comfortable with the shifting the power series, go back and look at my example. But for now, I'm going to say the end result of what happens is we end up replacing each n with an n plus 2, an m plus 2, and then an n plus 2. So I'm just going to write this right away as n plus 2. So this n becomes n plus 2. This n minus 1 becomes n plus 1. This an becomes a n plus 2, and this x to the n minus 2 becomes x to the n. Okay? And then minus n minus 1, a n x to the n, minus 2n a n x to the n, plus l plus 1, a n x to the n equals 0. So I'm not going to write these indices because they're the same as for all of them. So now I want to combine these into a single term, n equals 1 to infinity, and we have, now what do we have? We have n plus 2, n plus 1 times a to the n plus 2. And then what do we have left? So we have, let's see. So this is where my an plus 2 is. An is everywhere here. So what I'm going to do is I'm going to put an x to the n here, and I'm going to set this equal to 0. But now what we have is, let's see, do I want to make this plus or minus? I'm going to make this minus because we're going to set it equal to 0. So I'm going to say this is minus n minus 1 plus 2n minus L times L plus 1, and that whole thing should be AN. Did I get my signs right? Yeah, that's minus, this is a minus, that's minus and plus, this is a plus, that's a minus and minus. Okay, so this is what we have. Now we want to set this thing equal to 0. So let's set that equal to 0 and solve for an plus 2. So we get that an plus 2 equals, let's see, how do we want to do this? So let's move, basically let's just turn this minus into an equals. That's all that there is. And then divide through by this guy. So if we do that, we get, well, hold on, let's simplify what this is. So this is n squared minus n plus 2n. That's what this is. And what does that equal? So that's n squared minus n, which is n times n minus 1. Oh, that's convenient. We have an n minus 1 and an L times an L plus 1. So we have equals n minus 1 minus L times L plus 1. And make sure I did that. Oh, no, hold on. That should be a plus n and a plus n and a plus 1, and this is going to be a plus 1. Something seemed wrong. I thought both of these were the same, and they are. So on the bottom, we are going to get an n plus 2 and an n plus 1, and now we get an an. So this is our final solution. So once again, for every L is fixed. That corresponds to some harmonic or some vibration. For every L, we get a power series solution like this, and we get and that power series solution, the coefficients satisfy this recurrence relation. So if you think about this, what we actually get is this is generally a power series, except when n equals L, then this top thing becomes 0, and like we did before, we actually get a polynomial, and those things are called Legendres. Legendre's polynomial. And they've been well studied by physicists, by mathematicians. They have recurrence relations, they have formulas. But again, for each fixed L, there's going to be a Legendre polynomial of degree L that satisfies this ODE. So every ODE like this, Legendre's equation, it'll have a power series solution, and then it will have a polynomial solution of degree L. And this is actually technically what we are going to call in the next lecture this is going to have a singular point for reasons that I have not explained. So I will get into that in the next lecture. So there's a little bit more work to be done, and we may or may not cover that later in the class, depending on what material we get to. Okay, so stay with us. More on this coming up.